Welcome to the lecture for Psych 350 Personality. I'll be talking today about studying personality, how personality researchers gather information about people. We'll start off talking just a little bit about why research is important as a source of information, because it is just one source of information for theorists and for people to develop ideas about what people are like. But it's an important one for a couple of reasons. One, it can reduce the impact of personal bias. So if you're trying to come up with, well, this is what people are like, you could just kind of introspect and reflect and come up with your own theory. And if you had, I guess, a lot of power, you could impose your theory on others. But fortunately, for us, it's not quite the way it works. And instead, we have this tool of science where you can come up with your idea, but then it's subjected to a scientific method to see whether or not it's true. That way, just somebody's individual belief isn't imposed on others, but they're subjected to tests, so we can see, well, is this really how it is? So it can reduce the impact of personal bias. And notice I didn't put eliminate the impact of personal bias, because science is unable to do that, because it's conducted by people who have biases. So the questions that people ask, they ask based on their own personal bias. The way that they gather data, the way that they operationalize variables, the way that they measure things, is influenced by their own bias. But as a knowledgeable consumer of research, if you're aware of how to identify these biases and how those biases impact the conclusions you can draw, then you're going to be in a good place in terms of making sense of research. Another reason why it's important is when we conduct research in any kind of standardized way, it's possible to aggregate data. So across studies, one person found that shy children had shy mothers. Okay, and another study found that shy children had shy mothers. Now we can put those two findings together, and it has more strength than just one study by itself. Whereas if you don't use research, and you just kind of use people's ideas based on their experiences, it's not clear how typical those experiences are. Maybe comparing apples to oranges. With research, we have a way of making them all apples. So the aggregation of data, it kind of builds upon itself, is a helpful feature of empirical study. And then another really big reason why it's important to know how to conduct research, and for you especially how to make sense of and interpret research, is it has an increasingly large impact on public policy. Decision makers now are saying, well, what do the data say? Well, the data comes from research, so if you want to change the way that laws and policies are created and enacted, then you need to be knowledgeable about research, because it certainly could be misused if you're not, if you don't have an awareness of how it's supposed to be conducted. Okay. Okay. So research is an important source of information. Again, not the only one. You shouldn't live your life solely based on empirical data, in my opinion. But it should be, again, in my opinion, an important influence on what you believe to be true. Now let's talk for a minute about the logic behind research. It's really a combination of two types of reasoning. Inductive reasoning, where you start off with observations. You kind of notice things about people. Maybe you read about other people's observations, and then from those collective observations you you build up to some encompassing idea. Okay, I've noticed this happens a lot. Maybe this is generally true. Right? So we have some observations to ideas or theories, right? And a theory is just a conceptual framework, a way of making sense of disparate observations and talking about how variables are related. So you use inductive reasoning, and then the other part of that is deductive reasoning. So based on these ideas or theories, you generate testable hypotheses, and then you go and gather more observations to test those hypotheses. Right? So there's kind of the cyclical nature of science, where typically at some point in the line it starts with observation. Right? There's not people usually don't come up with theories out of thin air. They have some observations about people, about the world, and from that they use inductive reasoning to develop some theory. From the theory, you develop testable hypotheses, because you can't test a theory directly, but you say, if the theory is true, then I should see this. So that if-then statement is the hypothesis. If the theory is true, then this is what I should observe. But you can't stop there, right? You have to go and observe whether or not that actually, the then part, happens. So you gather observations in a kind of a testing setting, and you are going to either find what you said you were going to find, or you're going to find, well, no, it wasn't true. And then again, you don't stop there. Then you go back and say, okay, well, I confirmed what I expected to find. How does that relate to the theory? And it doesn't necessarily prove the theory, but it does support the theory. And an important thing to note here too, it doesn't even necessarily prove the hypothesis. It proves the hypothesis at that point in time with those people you studied, with the way you measured it. Right? So, yes, you found something, but how generalizable, what conclusions you can draw from that, depend to a great deal on the quality of your study, how you collected the data, which we'll get to later. So as you're kind of going through this process, you're always going to be revising theories, right? So you have observations to theory to hypothesis, back to testing the hypothesis via observation, reforming the theory, and to progress at a pace that is reasonable and helpful, you want to have a good theory, right? Because if you have a bad theory, you're going to have bad hypotheses, and then your observations may be meaningless. So what makes a good theory? Several things. Two of which that are addressed in your text are being parsimonious and being able to generate testable hypotheses. And parsimony is an important part of science, but it's often misunderstood. You think, okay, well, a good theory is a simple theory. So of the theories out there, whichever one is simplest is the best. Not exactly. That's not what parsimony means in terms of science. Parsimony means of the theories that explain the most, which is the simplest. So if there are two theories, and one's simple, one's complicated, but the complicated one explains more stuff, explains it better, then the complicated one is better. Right? But if the complicated theory and the simple theory explain things equally well, they predict equally well, then you choose the simpler theory. So it's not just go with simpler, it's go with the simplest of the best. Okay. The second part, in terms of generating testable hypotheses, and this relates to, if a theory involves some process that's not observable, some sort of supernatural force, then it may not be very useful to scientists. It may be a good theory in terms of it may be correct, but if it can't be tested, then scientists don't know what to do with it, and it kind of falls outside their realm and falls into the realm of philosophers, theologians, what have you. For scientists, theories must be able to generate testable hypotheses, so they have to have observable processes. Okay. As I alluded to earlier, there's an impossibility of proof and disproof with theories. You will never prove a theory to be true, and you will never disprove a theory to be true. All you can do is provide more support for a theory, or provide less support for a theory. And over time, as more studies are conducted, if a theory is supported more and more, then we're more confident that it's true. But we're never going to say, oh yeah, it's definitely true. And part of it has to do with the way we do our statistics, part of it has to do with the logic. But you kind of know that you can't prove beyond a reasonable doubt that something's true. And this kind of goes to the philosophical idea that we can never know the capital T truth. We can know the lowercase t truth. We can kind of know what we observe, but to know if that's really true in the grand scheme of all things is beyond our knowing. But because it's impossible to prove or disprove, and we need to support, when we look at how well a theory is supported or not supported, it speaks to the importance of replication. Right? Replication means if somebody finds something, we don't say, okay, well they found it, it must be true. We're done with that. No, you got to say, well, can somebody else find it? Maybe it was a fluke, because with the statistical methods we use, flukes can be statistically significant. Right? People can find something and it's not really true. or they just happen to find it with that group of people at that time for some unknown reason, randomness. Right? That can happen. So it's important to replicate things because findings could be due to chance, but also because findings could be limited to some aspect of that study or the people that they studied. So it doesn't apply to everybody. So we need to find out, okay, well, how well does this theory apply to other people, other situations across time, right? Because it's not the research findings don't apply to people, it's the theory that we're trying to apply to different people at different places, different points in time. And to do that, we have to replicate a finding, a study's finding, in different settings with different people and measuring things different ways. Okay. Now hopefully most of you are familiar with many of these terms. Just in case it's a quick review about the language of research. We can break down research into kind of a couple of different types. One of the key types is experimental research, and this is research aimed at looking at causative relationships between variables. You know, does one thing cause another thing? Changes in A, do they cause changes in B? Right? And when you're doing experimental research, you're going to have an independent variable, right? And this is the variable that you manipulate as the experimenter. You have to have the power to assign people to levels of the independent variable. So if I had a research question, it was, you know, what impact does the size of a crowd have on a person's anxiety level? Right? If I'm going to do an experimental study looking at that, I'm thinking, okay, well, crowd size will be my independent variable, right? But I have to manipulate that, and I have to manipulate crowd size by having two different crowds, and I create the crowds, and I assign people to be in one crowd or the other crowd. If I don't have the power to assign people, if people can choose by themselves, it's not an experiment, right? I have to have the power to assign them to levels of the independent variable. And I have to do it in such a way that the individuals I'm assigning, I assign them randomly, right? So they have an equal likelihood of being assigned to one crowd or the other. Right? So I don't assign, oh, first half here, second half there. That's not random, because people in the first half might be systematically different than people in the second half. So I come up with some random assignment. I don't have to have random sampling, but I have to have random assignment to levels of the independent variable. So I'm manipulating that. I'm making you, as a participant, experience one level of the independent variable or the other. It's not up to you to decide what level you get. It's up to me as the researcher. Okay. And after I do that, then I'm going to measure a dependent variable. And the dependent variable is the one that you think depends on what level of the independent variable somebody is in. So in this example, that would be anxiety level, because we think anxiety level depends on the size of the crowd that you're in. Right? That's why it's the dependent variable. So this is a variable that's measured, and there are a variety of ways to measure anxiety. We can take physiological measures. We could ask people to self-report how anxious are you. We could just observe people and look for signs of anxiety and get multiple raters to rate them and see if all the raters agree. But find some way to measure anxiety level, and that's your dependent variable. And then you're going to look, apply some statistical analysis to see, do these two groups differ? Do the people that were in the big crowd group versus the small crowd group, did they have different levels of anxiety? So, do people differ on the dependent variable depending on what level of the independent variable they received? Okay? And that's experimental research in a nutshell. A different type of research would be correlational research. Here you're still looking at a relationship, but it's not necessarily a causative relationship. You might think that there's a causative relationship, but you can't study a causative relationship via correlation research. Right? You can't, if you conduct correlation research, you can't conclude from that, okay, A caused B. But you can conclude A was related to B or A was not related to B. Okay? So it's a different type of research. We have some different terms. You have a predictor variable. This is the variable that you're predicting with. So usually you're saying, okay, I'm trying to predict something with something else. So here I'm trying to probably predict anxiety with crowd size. So here, crowd size would be my predictor variable. Right? I'm predicting with crowd size. So I'm not manipulating it now. So maybe I just go to a concert, I get there early, nobody's there, and I start measuring how big the crowd is. There's 10 people there. Okay, now there's 20, now there's 30, now there's 40, and I'm measuring at multiple points in time as it grows and maybe even shrinks later on. And then I'm also measuring, which is all about measuring all your variables, a criterion variable. This is the thing I'm trying to predict some outcome. The outcome would be anxiety. And again, I can use the same types of measurements as I would in experimental research. For the dependent variable, criterion variable is the analog of that in correlational research. So I'm measuring people's anxiety as the crowd gets bigger and smaller. Right? And I'm looking to see if there's a correlation between those two variables. So as crowd size increases, does anxiety go up or does it go down? As the crowd size decreases, does anxiety go up or does anxiety go down? Pretty straightforward. And typically we think about, in correlational research, linear relation to variables, but there are other kind of statistical approaches to look at even non-linear relationships, curvilinear relationships, for example. And a third type of research I wanted to touch on would be quasi-experimental research. This is when you're trying to look at causation and you're employing a lot of experimental control, making it very experiment-like, but you can't manipulate the independent variable for some reason, either ethically or practically. It's just not possible. The example I always give is looking at the effects of being widowed on depression. You can't take away someone's spouse. You can't assign people, okay, you're in the widow group, you're not in the widow group. I'm going to kill your husband, I'm not going to kill your husband. Ethically, practically, you can't do that. But if you want to look at the effects of widowhood, you could compare two groups of people, and if you exert lots of control, then it starts to become quasi-experimental, almost experimental. So here we're typically dealing with groups, right? We're correlation research, we're not dealing with groups, we're measuring variables and looking at a relationship. So quasi-experimental, we're looking at groups, but we're not creating the groups. So maybe with our example, I go to two different events, one where there's kind of a large crowd and one where there's a small crowd, a big festival concert versus a show at the Paramount in Austin, little kind of intimate theater, right? And I look at the anxiety in people in those two crowds, the big crowd people and the small crowd people. And are they different in anxiety? So I didn't assign them to go to one show or the other. They just went themselves. They self-selected. And then I measured their anxiety, with the same type of ways I would measure with experimental research or correlation research. So again, I would have this quasi-independent variable, which would be type of show they went to or crowd size that they attended, right? So very similar to the independent variable before, but I didn't assign it. And then again, I would have a dependent variable, which would be the same thing. But it's important to remember that the interpretation of the results from these different types of studies differ. Right? From experimental research, you can make causative interpretations. Right? If you do a good experiment, you have good internal validity, then you can say, the difference that I observed in the dependent variable is attributable to the difference that people received on the independent variable. Right? And that's the main reason to do experimental research, is to be able to make those conclusions. For correlation research, you can't make that interpretation. So let's say that there was a relationship between crowd size and anxiety, and maybe one you wouldn't expect, maybe an inverse relationship. So as the crowd size increased, people became less anxious. Oh, wow, okay, so being around more people makes people less anxious. Interesting. Well, you can't conclude that, and the two main reasons you can't infer causation from correlation, we've heard that before, are directionality and the third variable problem. So in terms of directionality, that's saying, well, if there's a relationship, you don't know if A caused B or B caused A. So as the crowd got bigger, people got less anxious. You might think, okay, well, getting more people there made people less anxious because they felt, safe from the outside world because there's safety in numbers. Some explanation. Well, it could have been that as the crowd, people in the current crowd got less anxious, more people on the periphery joined the crowd. Oh, that looks like fun. No, they're not very anxious. Whereas when the crowd is small, people look anxious, like, oh, that doesn't look like a good time. So as the people got less anxious, the crowd got bigger. Right? So A to B or B to A. You can't conclude from a correlation study. And then the third variable problem is the relationship between A and B could be explained by some third variable that is related to both of those. Right? So maybe maybe as the crowd got bigger, there were more people present smoking pot, and then the marijuana smoke in the air made people feel less anxious. Right? So the marijuana contamination in the air is actually the causative variable. It caused the less anxiety, and it was caused by the increased crowd size. So there's a third variable that explains the relationship between the other two. So cannot infer causation from correlation. Don't do that. And then for quasi-experimental research, we can't infer causation because we have non-equivalent groups, right? With experimental research, when we're randomly assigning people to groups, the assumption is that by randomly assigning people, then those two groups differ in no way other than the independent variable, right? Because if there's some really anxious people and some really not anxious people in our study, if I randomly assign them to groups, I should have equal numbers of really anxious people in each group. Right? So the groups shouldn't differ in their pre-existing levels of anxiety. Right? With quasi-experimental research, if I don't assign you to the independent variable, I can't be as certain about the quality of groups. So it could be that the two groups differed already before they went into the crowd. Right? So maybe people who go to smaller crowd events are wealthier and therefore less anxious because they got a lot of money in the bank than people who go to large crowd events. So maybe there's other variable that explains the anxiety difference, and it's not the crowd effect, it's some other thing that they were already different on before we observed their anxiety. Okay, so that's a very quick review of a semester in research methods. Let's move on to talking about the case study method, which is obviously an in-depth study of an individual, or sometimes a few individuals. Sometimes it's a group, but not very many people. And typically this is a non-experimental type design, typically an observational design. You can do experimental type of stuff with a case study, some kind of single subject design stuff, which if you take grad research methods with me, I'll be glad to tell you about. But for here, generally you're just observing one person or a couple of people. So if we think back to the types of reasoning we thought about before, would this be more inductive or deductive reasoning? Right, more inductive reasoning. So really you're gathering observations to kind of come up with a theory about people. And probably you have some theory in mind, but you're not imposing that theory on the individual. So the case study method, frequently used in the development of personality theories, long history of it, but it does have some limitations in terms of going forward. The external validity, which has to do with the generalizability of the knowledge you gain. So if you found that this person was this way, okay, well, does that apply to anybody who's not that person? You know, you only had one person in your study. How do I know that that isn't what you found isn't particular to them, and that it is reflective of the human condition? Right? That's a limitation. Also, there are problems in terms of the internal validity, which is internal validity is your ability to draw cause and effect conclusions. Right? So if you're observing somebody in a case study and they're maybe really shy, stick with our shyness, they're really shy, and you try some intervention, exposing them to group settings under the influence of ecstasy, and you find that they become less shy over time, and you withdraw the ecstasy and they remain less shy, then you've shown that this kind of cause-effect relationship, that you can treat shyness pharmaceutically. Well, that's a single person in your study, and so we can't be very confident that there is a cause-effect relationship there between the drug exposure and the change in shyness. There could have been other things going on in this person's life, and so because of that, we're not very confident about the cause-effect relationship. So there's limited internal validity. And then, of course, obviously, there is the potential for researcher bias. Doing a case study, making observations, requires some interpretation of those observations. You have to organize them into ideas. And so, two different researchers observing the same person, observing the same exact person, the same behaviors, might come back with very different interpretations. Right? They might see different behaviors because they're looking for different things. If they're working from two different theoretical points of view, they'll perceive things differently. And so the conclusions drawn from case studies are often biased, not say biased in a bad way, but they're influenced by the beliefs, the theories of the person conducting the research. Nonetheless, has been used extensively and still has some value going forward because of its strengths. The primary one would be the ability to generate testable hypotheses. Right? We talked above about how this is going back to inductive reasoning, which is a great way to generate theories and kind of hypotheses. Well, I noticed this happened with this one person. I wonder if that's true with other people. Right? And especially process-oriented stuff, it's difficult in large groups to observe process, to see how things happen. You can see difference pretty easily in groups, but watching a process of how something changes over time, really hard to do well with large groups of people. But you can do that with an individual, develop some theory and some hypotheses about the process, and then go back and test them with larger groups. Also can be valuable with kind of rare phenomenon. Individuals who have particular personality traits or types that you don't see very often. Sometimes those can be really informative, and you can't do a large-scale study of those individuals. So if you can only have one person, do them in depth. So you take that case study method. And then another thing that people don't often think about is sometimes it's important to just demonstrate that something is possible. So not that it will always happen, but that it can happen. And usually we do this to show that something can happen before we're saying, well, how often can it happen? So we're trying to change someone's personality, maybe trying to make them less neurotic. We try something, and we're not going to maybe try it with 100 individuals. We're not sure if it works, because it might be wasting a lot of time and resources. We'll try with this one individual, see if it can work. And say, okay, well, it worked with this individual. Now let's try it with more people and see if we can show that it works with a variety of people with different experiences. Right? So it's often a good starting point. Okay, so whatever type of research you do, typically there'll be some data generated, and there are lots of different ways to analyze, to make sense of data. One way, this is just one way, the most common one is null hypothesis statistical testing, right? Where you are making you're testing the null hypothesis, the hypothesis that there's no effect, right? And so you're looking at if there was zero relationship, zero effect, what are the odds I would find the data that I found, right? So you get a group difference of 5 points. So if in fact the two groups were exactly equal and the difference was 0, what are the odds I would get a difference of 5? And that's what null hypothesis statistical testing does. And you generate a p-value, remember that term, and that is the probability of finding what you found if there was no relationship. Okay, so if you get a p of 0.01, that means that, okay, if there was no relationship, then I would have only found the difference that I found 1% of the time. Okay. So what that means is, so if these two groups are different, and you found a difference of 5 points, and in reality there's a difference of 0.0001. Okay, so they're different. The difference isn't 0; it's 0.001. Then the null hypothesis is false, and you're always going to find a statistically significant effect if you have enough people in your sample. Okay? So null hypothesis statistical testing is helpful, but it's limited because the null hypothesis in reality is probably almost always true. So we can't just like, okay, what's statistically significant, then great. Well, it's statistically significant. How significant is it? And the p-value doesn't tell you how significant something is. That's a misapplication of statistical logic. So a p of 0.001 isn't more significant than a p of 0.05. Not at all true. Don't ever say that to anybody. So if we can't rely on p-values, we have to look at something else, and that something else that we look at, increasingly so in our field, would be effect sizes and confidence intervals. So we look at, okay, it's statistically significant, so the difference isn't 0, the relationship isn't 0. How big of an effect is it? How big of a relationship is it? And an effect size is just a way of standardizing across studies. So you use this measurement, this type of data, whatever, putting it all in the kind of the same numerical language to say, okay, well, that's a small effect, a medium effect, or a large effect. It's just a mathematical way of doing that. And then we say, okay, well, that's a big effect size, you account for a lot of the difference with your variable. Right? And the confidence interval is just a visual way of doing that to see how different two groups are given their level of variability. If there's a lot of variability in two groups and they're only a little bit different, they're probably really not really that different. But if there's not much variability, so you've got an average of 9 and of 10 in your two groups, but everybody in one group was 9 and everybody in the other group was 10, then that's a reliable difference, right? They both have really small confidence intervals, they don't overlap. That 9 and 10 are probably different. But if you have a group of 9, average 9, group of average of 10, and the 9 people, there's some that are 1, there's some that are 18, it's all over the place. The average happen to be 9, and then the 10 group, same thing, they're all over the place. The average happen to be 10. Those two groups, probably not really different. Their confidence intervals are going to overlap. Okay. In terms of statistics that you may generate, one of the most common ones that you'll read about will be the correlation coefficient, and there are different ones. The most common one we'll see would be the Pearson R, and it's a measurement of the linear relationship between two variables. So as one changes, what happens to the other? Does it go up or does it go down in a linear fashion? In this correlational coefficient, can range from -1 to 1. If there's no relationship, the correlation coefficient is 0. If there's a strong positive relationship, so as one goes up, the other goes up, or also positive relationship would be as one goes down, the other goes down. So if they co-vary in the same direction, one moves one way, the other moves that same way, that's up towards the +1. A perfect correlation would be +1. Perfect positive correlation. A perfect negative correlation would be -1, and that's when they move in opposite directions. So as one goes up, the other goes down. As one goes down, the other goes up. Right? So if there's an inverse relationship, a negative relationship is closer to -1. And the further away a relationship is from 0, the stronger it is. Right? So closer to 1, a stronger positive relationship. Closer to -1, a stronger negative relationship. Closer to 0, a weaker relationship in general. And as you may have discerned from my statement above about effect sizes, it's important to realize that statistical significance is not the same thing as clinical significance or real-world significance. Right? Just because somebody found something that's statistically significant doesn't mean that it's significant. It's not necessarily important. Right? Statistically significant means that two groups didn't have the same exact mean. They differed by some amount, and that's really all it means. Okay? So don't get too caught up in statistically significant findings. Right? They may or may not be significant. One more kind of point I want to make about the statistical analysis of data before moving on would be that data do not lie. Right? The numbers are the numbers. People say, oh, well, you can use statistics to say anything. Yes, you can, but the numbers don't lie. People lie. People can misinterpret the data. They can overinterpret. Right? They can take a study that was done with college students in Texas and apply it to kindergartners in Portugal. That would be a misapplication of data. Right? Those two groups are pretty different. What you found here may not apply to that other group. That's an overinterpretation. Studies can be done poorly, which limits the interpretation of the conclusions, the applicability of the conclusions. But the data, so if they found, okay, there is a statistically significant between two groups in the study, then yes, that's true. This group scored higher than this group on this test. Now, whether or not that test measures what they said it measures, whether or not that difference is important, that's for you to figure out and think about. You can't just accept, statistical significance and reports of studies as gospel. You should always go in questioning and be critical of it and say, well, you say that. How certain am I that your conclusions are supported by the data you have and the way that you gathered that data? Right? So go in skeptical. Scientists won't be offended. That's what they hope you'll do. What you should do. Okay. It's also important when talking about researching personality to talk a little bit about the assessment of personality, because most of the research in personality involves measurement of variables, an assessment of personality variables, because we can't very well manipulate people's personalities. We can't make you more outgoing or less outgoing. Well, we can try, but we can't knowingly assign you to levels of personality. And so typically we test personality. It's important to be familiar with some of the key concepts of assessment. One of them would be reliability. So it's important that whatever way you're using to assess a variable is reliable. So, and there's a couple different types of reliability. The one that makes the most sense to most people would be test-retest reliability. So if I measure your personality today and I measure your personality in 2 weeks with the same instrument, you should get pretty much the same score. Right? And if you do, that's test-retest reliability. And that's generally a good thing, depending on how stable you think the construct is. So some things, if a construct isn't expected to be stable, then you won't necessarily have good test-retest reliability over large periods of time. So like, think about state anxiety versus trait anxiety. State anxiety is kind of how anxious you're feeling right now, and it goes up and down. Like, oh, I've got a test coming up tomorrow, a little anxious. A couple days from then, you're going on vacation, I'm not anxious at all. That's your state level anxiety. Your trait level anxiety is kind of across time. You're more anxious of a person or less anxious of a person. Now, if you have a measure of state anxiety, it may not have good test-retest reliability if you test time 1 and then time 2 is 3 months later. Something very different may be going on in your life, and you're not current. You were anxious at point 1, you're not anxious at point 2. It's a good measurement, but it doesn't have test-retest reliability because it's not expected. So test-retest reliability is important, but it's important in a time frame that matches onto and is consistent with the way you conceptualize that variable or that construct. Okay. Another type of reliability that would be harder to understand would be internal consistency. And this is usually when you're asking multiple questions about the same thing. So if I have a test of ego strength, right? It's kind of psychoanalytic concept. Then all the questions I ask should really be about ego strength. And if I have, so somebody who has strong ego strength, if they answer all the questions one way, indicating strong ego strength, but then one question they answer the other way, indicating weak ego strength, that question doesn't fit with the others, right? The system may not have good internal consistency. That one question may not really be measuring ego strength if it doesn't follow the other ones, if it's not answered in the same way. And there are ways statistically of measuring this, many of them not great, but we can get an estimate of when people answer this assessment, do they answer all the questions that should be answered the same way in the same way. Okay. So reliability is good, it's necessary in assessment, but it's not sufficient. Right? The gold standard is what we'll talk about next, validity. And to have validity, you must have reliability. You can't be valid if you're not reliable. But reliability in and of itself isn't enough for validity. And so if you have a scale at home and you weigh yourself, and every day you go in and it says 40 pounds. And every single day, 40 pounds. That's a very reliable scale. But you probably don't weigh 40 pounds. So it's not a valid measurement of your weight, but it is a reliable measurement. So you can be reliable, but not valid. But if you have validity, that assumes you have reliability. Because if you go in and you weigh 40 one day, 100 the next day, 70 the next day, that's clearly not a valid measurement of your weight because it's all over the place. It's not reliable. So reliability necessary, but not sufficient for validity. When we're talking about validity, we're talking about construct validity. And construct validity is, are we measuring what we say we're measuring? And this construct is this idea, right? Like intelligence or openness or extroversion, right? These are things you can't show somebody your intelligence. You can't show somebody your openness to experience. Here it is, right? It's not tangible. It's this construct. It's our understanding of human experience. And because of this understanding of human experience that isn't directly observable, right? Like it's not an atom, we have to take into account, okay, this is what I think this idea is. I'm trying to measure it. Is my measurement consistent with the way I say that this thing is? And that's construct validity. Are you measuring what you say you're measuring? different aspects of validity that will influence construct validity. So everything's feeding back into construct validity. That's the main thing. The least important of which is face validity. This is, does something look valid? So if you're asking questions about openness to experiences, are you open to trying new things? That's a very face valid thing. Oh, I see what you're trying to measure. And really the only reason that you might worry about face validity is if you have a test that has really poor face validity. People may be confused about what you're asking about, and may not, if they're trying to guess what you're asking about, they may answer in kind of idiosyncratic or odd ways. But generally, face validity, not that important for researchers. What is more important would be congruent validity, or what I used to talk about as being convergent validity. Your text uses some terms that are different than what are talked about in most other texts. But same thing here, congruent, convergent validity is your measure of aggressiveness. Does it relate to other people's measures of aggressiveness? So if you have a participant come in and take your measure of aggression and they score highly, will they score highly on other people's measures of that same construct of aggression? If they do, then you have good congruent or convergent validity. Those findings converge. And that will be good, but you also want good discriminant validity, also called divergent validity. So you have this measure of aggression, and somebody else has a measure of psychopathy. Somebody, how are you a psychopath? And if somebody comes in and they score high on your measure, and then they also score high on that measure, you're like, that's may be good, may not be good. But if everybody comes in scoring high on your measure, also scores high on psychopathy, and everybody who scores low on your measure also scores low on psychopathy, that's a problem, because psychopathy and aggression are two different things. Some psychopaths may be very aggressive, some may be not aggressive at all. But if everybody that looks like a psychopath looks like they're aggressive on your tool, those things, that's bad. Those things should diverge some. They shouldn't be perfectly related. If they are perfectly related, then you're probably measuring psychopathy and not aggression. So you're not measuring what you intended to measure because it's relating to things too well that it shouldn't relate to. Okay. And the last type, your book talks about behavioral validation, which is typically referred to as criterion validity. And this is, so the other two, congruent and discriminant validity, are about performance on one measure, how it relates to performance on another measure. Behavioral validation, or criterion validity, says performance on your measure, how does it relate to some behavioral criterion out in the real world? So if I have measured your aggression and you score high on aggression, then I should see you've got multiple arrests for aggression, or I should observe you on the playground and see you pushing other kids, right? So those things are my findings are validated, or I find a relationship between the performance on the measurement and the behavior that it should indicate, the criterion, the outcome that it should indicate. Okay. So all those things are factors in terms of looking at the validity of a measurement. And again, this could be a paper and pencil measure, it can be an observational measure. Any way that you measure something, you can look at its validity and reliability. And when you look at validity and reliability, you're looking at the psychometric properties of an instrument. You hear that term, oh, it has strong psychometric properties, or weak psychometric properties. That's talking about the reliability and the validity. And whenever you're looking at studies and trying to figure out if the conclusions are valid, this is one of the key things to look at is, well, how did they measure the things they were measuring? And did they measure them in a valid and reliable way? Okay, so summing up, what you should know after all this. You should know why research is important. Right? We've talked about a couple of reasons. You should know generally the logic behind the approach to research, how the thinking goes in advancing science. You should be familiar with the differences between experimental and non-experimental research, especially the difference in the kind of conclusions that you can draw depending on what type of research it is. You should be familiar with, obviously, the case study method, the strengths and weaknesses, what it can do, what maybe it can't do so well. You should be generally familiar with how data are analyzed in the null hypothesis statistical testing approach, and kind of what statistical significance means and what it doesn't mean. And finally, you should be familiar with the key concepts in assessment: reliability and validity, the difference between them, and why they're important. All right, take care.